All right, so we completed 7-3 part 1, which was finding volumes by using known cross-sections. And that is going to lead directly into 7-3 part 2, which is finding volumes using the disk method. So what I have here are 4 different images, and I'm going to use the same method to find the volumes of each of these 4 different shapes. Now, I think you can agree that these 4 different shapes are all a little bit unique, but the way in which we're going to find their volumes has one unique theme. And the theme is that it started off with a function. Each one of these shapes started off with a function, like this or like this. And that function, so this one here began with just this arch. In fact, let me use a different color there. So this right here, this arch right here, is f of x. And what we did is we took that arch and we rotated it around an axis. Here, I had this arch here. This is the same function. And I rotated it around this line down here, which I know it's hard to see, but it's around this line y equals k. And then in these 2 pictures, I have this right here is the function. It's just a function in terms of y. So it's g of y. And here's a similar function right here, g of y, being rotated around a vertical line. So what's happening here, and bear with me for a second, I'm going to zoom out. What's happening here is we began with a curve. So imagine that this curve is defined by a function. In fact, it's a half circle. So let's go ahead and imagine that the equation of this circle is the square root of, and then maybe 16 minus x squared. Just imagine that. That's the equation of this half circle here. And it's sitting along the x-axis, okay? And what we're going to do is we're going to rotate that 360 degrees around, you can see that, it's kind of hard to see it all, but it's around the, let's see if I can go this way. So 360 degrees around the x-axis. What's been created is a 3-dimensional shape. A 3-dimensional shape, okay? And if I were to slice into this 3-dimensional shape, I would see that the cross sections are circles. So let's look at what that would look like. So here's sort of half of the same shape as before. And having been rotated around, this one's a little bit falling apart. So if I were to look dead on, like if I were to slice open my original shape and look dead on at it, I would notice a circle. I would notice a circle because the shape was formed by rotating. That motion of rotating creates circular cross sections. So you can see here, this curve was rotated around the x-axis, creating circular cross sections. So we're going to use the same principle of finding a volume by using cross sections, and these are all going to have circular cross sections by virtue of the fact that they rotated. That rotation is what creates the circular shape. Now again, the circular shape is a cross section. It's what you'd get if you sliced down the middle of the shape. You would be looking dead on at a circle. And that's the same with this one here, has a circular cross section. This one here has a circular cross section, and so does this one. They all have circular cross sections. So in general, the volume would equal the accumulation, so in this case from A to B, the accumulation of all of those circles, pi r squared, in this case dx, because I'm integrating with respect to x, whereas in this case would be dy, since here I'm integrating with respect to y. So this volume right here, so this is when you're integrating, or sorry, how about this? You integrate with respect to x when you rotate around a horizontal line. So this is for rotating around a horizontal line. Okay, and then this one here, these have been rotated around vertical lines, so there's a little slight difference there. Notice it's still pi r squared though, because this is still an area of a circle, because basically volume is the accumulation of all the areas of the cross sections, and since the cross sections are all circles, the areas of the cross sections would just be pi r squared. It's just in this case, I'm integrating with respect to y. So volume would equal the integral of all of those areas of circles with respect to y. Okay, so now let's look at these unique pictures here. See if we can make some sense out of them. So notice with this first picture here, the radius is going from the x-axis to the top of the curve. And that radius for each circle is going to change depending on what x I'm at. If I were at this x right here, the radius can only go up as high as f of x. So in this scenario, my different radiuses are basically just equal to the height of the function, because they just go from the x-axis up to the top of the function. So in this particular example, it would go from a to b, because that's the left and right point. So I integrate from left to right, pi times f of x squared dx. Whereas in this case, the circles are being stacked vertically. They're perpendicular to the y-axis, so the radius is going to go off to the side like that. The radius of each of the unique cross sections is going to go off to the side. So what happens is now that radius is going to be in terms of y. So it's like you go up a distance of y and you go out, and that value right there is g of y, because it's a function of y. So this radius for this particular example can only go out as far right as this curve went out. And this curve is defined as g of y. So this volume would go from C to D because it goes from bottom to top. You're accumulating all those different areas of all those different circles. So it's pi times r squared and then dy. So these are the nice easy ones because this one went around the x-axis, this one went around the y-axis. Okay, but these here, slightly different. Here's the same curve f of x, but instead of being rotated around the x-axis, it's rotated around this line way down here at k. So if you look at it, the distance from the x-axis to the top of the curve, that's only part of the radius. That part is f of x. The distance from the x-axis to the function, that's f of x. But then there's all this part as well. Well, that would have to be k, the distance of k, because that's how far down this line went. All of that together makes up the radius of this circular cross-section. So in this scenario, my radius was the distance from the x-axis to the curve, f of x, plus the distance from the x-axis down to this number k. So then this volume would be, again, going from A to B, from left to right, pi r squared, which in this case is f of x plus k, quantity squared, dx. So sometimes we have to get a little more creative with what our radius is going to be if it's not centered on the x-axis or the y-axis. Okay, then over with this one, notice how the distance from the y-axis to the curve is only part of the radius. That distance is g of y. I can't really fit it in there, but I'll put a little arrow. That distance right there is g of y. And then from the center of the shape all the way to the y-axis, that would have to be a distance of h. So to go all the way from the center of the shape all the way to the edge of the shape would be a total of g of y, which is the distance from the y-axis to the edge of the curve, plus h, which is the distance from the y-axis out to this line at h, at x equals h. That's our radius. So then the volume would be the integral from c to d of pi times g of y plus h quantity squared dy. So those are sort of 4 generic examples of how that could happen. What we're going to do now is actually apply it to a specific example here in example 4. Okay. So we're going to go ahead and find the volume generated by revolving about the x-axis, the region bounded by this graph right here. So the graph of square root of x plus 1, that's just this part. And it's going to stop at the line x equals 5 because it told us. So it stops at the x-axis and stops at the line x equals 5. So it's just from here to here. And again, this curve has been rotated around the x-axis, creating these circular cross sections. So it would look something like this. Okay, we have this shape right here, just kind of similar to this shape right here. We just have this curve, just like this right here. We take this curve, we rotate that around the x-axis, and what happens is it creates a 3-dimensional object. So let's zoom out a little bit here. It creates this 3-dimensional object, which if you sliced it open, would have circular cross sections. Okay, so you have to kind of imagine if this were just perfectly round. It's a circular cross section, it's a 3-dimensional shape, because all this volume has been accumulated by rotating this once 2-dimensional shape around the x-axis. Okay, so I'm going to zoom in here. Okay, so I want to find the radius. My job here is to figure out what would the radius be of each of these circular cross sections. Now these cross sections, because it rotated around the x-axis, the cross sections will be perpendicular to the x-axis. So circles will be perpendicular to the x-axis. Okay, so I have to imagine I'd have, like, you know, depending on where x is, if I sliced here, for example, I'd have that circle. Or if I sliced right over here, I'd have that circle. The radius is going to be really small over here and really big over here, and it's based off of the height of this function. So the radius is going to go from the center of the shape, which is on the x-axis, up to the top of the curve. So it's basically going to be the square root of whatever x is minus 1. It's the height of the function. It's the value of the function. So the radius is basically equal to the square root of x minus 1. So then the volume, or actually I should say this, the area of each cross section is equal to pi r squared. And so the volume then would be the accumulation of all the area from 1 to 5 of pi times that radius squared. And then integrating with respect to x, since we revolved around a horizontal line, specifically the x-axis. Okay, so we're going to go ahead and simplify this a little bit. I'm going to pull the pi out because it's a constant, and sometimes it's easier to just pull the constants out. I'm going to square this and makes the square root sign go away. So then this becomes pi times x squared over 2 minus x, evaluated from 1 to 5. So then that would be pi, well, maybe we'll think of it as pi x squared over 2 minus pi x, evaluated from 1 to 5. So that'd be 25 pi over 2 minus 5 pi minus, let's see, 4 pi over 2. Oh, no, that's a 1. So 1 pi over 2 minus pi. So then I have 25 pi minus 1 pi over 2. That's 24 pi over 2. Then I have negative 5 pi plus pi. That makes negative 4 pi. And then this becomes 12. So 12 pi minus 4 pi, and we get 8 pi. And that's our answer for example 4. And that would be in cubic units because we just found a 3-dimensional volume. Okay, so I'm going to have you guys try one. I want you to pause the video right here, give this one a shot, and then come back in a second and check and see how you did. Okay, so let's see what happens here. Basically, when you graph this, we can we're just going to go from 0 to pi over 2. Maybe I'll just go ahead and plug in some points. So if I plug in 0 in there, cosine of 0 was 1, the square root of 1 is 1. Pi over 4 would be pretty hard to evaluate. Maybe we could evaluate at pi over 3. So cosine of pi over 3 would be 1/2. The square root of 1/2, well, that would be bigger than 1/2, so I don't know, a little bit larger than a half. And then if I plug in pi over 2, cosine of pi over 2 is 0, square root of 0 is 0. So basically, there's our shape. And we're going to revolve it around the x-axis. So what happens is it revolves around this way. And so this comes down here, and you have all these circular cross sections. So the radius basically can only go as high as the function goes. So the radius at any given x can only go as high as the function goes. So the radius is equal to the square root of cosine x. So the area of each cross section is equal to pi r squared, which is equal to pi times the square root of cosine x squared. And we're gonna go from 0 to pi over 2. So basically the volume is equal to the integral from 0 to pi over 2 of pi times basically cosine x dx. And then after doing some work, you should get the value of pi. So hopefully you guys did a good job on that one. We're going to move on now to integrating with respect to y. Oh, actually, no, sorry, we're still doing, yes, we are integrating with respect to y. Okay, so with example 5, we're finding the volume of a solid generated by revolving about the y-axis. So that means our circles will be perpendicular to the y-axis. Okay, the region in the first quadrant, so that's this guy right here, bounded by the graph of y equals x squared. That's why we have the parabola. But we're just looking at the part in the first quadrant because they told us to. It's also bounded by the y-axis, so we stopped it here, and the line y equals 6, so we capped it off here. So really it was just this part of it. This part of it. And then it revolved around the y-axis, creating this bowl-like shape, which again, if you sliced into this, you would have circular cross sections. It's just now the circles are perpendicular to the y-axis, meaning the radiuses are jutting out to the side. So the radius is going to be described in terms of y, which this picture has nicely sort of already done for us. They solved in terms of y. So if you plug in a y value, you would get back the square root of that y value. That would be how far out the radius could go. So the radius is equal to the square root of y. The area of each cross section, each circular cross section, is equal to pi r squared, which in this case is pi times the square root of y squared. And since I'm integrating with respect to y, we're going to integrate from bottom to top, from 0 to 6. So the volume is going to be the accumulation of all that area from 0 to 6, pi times basically y dy, because the square root of y squared is y. Okay, so I like to pull the constant out because that makes it easier for me to integrate. So then this is just pi times y squared over 2 from 0 to 6. So it's basically just 36 pi over 2 or 18 pi. So that's our answer with example 5. That's integrating with respect to y. So again, just to review, with respect to y, you integrate from bottom to top versus left to right. And your radius has to be in terms of y. This has to be in terms of y. So if they give you the function in terms of x, you have to solve for y. Okay, then example 6 is kind of one of the more complicated ones that we looked at earlier, where you're not revolving it around an axis, you're revolving it around some other line. You're going to have to be very creative in how you define your radius. So this one asks us to find the volume of the solid generated by revolving about the line y equals 8. So this is what we're revolving around. The region bounded by the graph of y equals x squared plus 4, so that's this parabola, and the line y equals 8, that's this line. So really it was just this part of it. Okay, and we flipped that around the line y equals 8, and so that's what created this part, was just the act of rotating it, and that's what creates these circular cross sections. Okay, so we need to be very creative in how we define that radius. Okay, so we have the radius of this, we'll just go ahead and use this one here. Okay, actually it'll probably be easier if we look at it in terms of the x-axis. So let's look at it, let's have it go down this way. Okay, notice that the distance between the line y equals 8 and the x-axis, that distance is 8. And notice that the distance from any point on the x-axis up to this curve would just be x squared plus 4. So this distance right here from the x-axis up to the tip of the curve would be x squared plus 4, because that distance changes depending on where x is. So that distance will just be described as x squared plus 4. Okay, so the radius, notice it goes from the line y equals 8 and goes down to the curve x squared plus 4. So you could say that the radius is 8, whoops, which is the total length, minus x squared plus 4. So it's the height from the line to the x-axis minus the height from the curve to the x-axis. That would leave over the radius. The leftover would be the radius. So again, you take 8, which is from here all the way to there. Take the height of 8 from there all the way to there. Subtract the height from the curve to the bottom, and what you have left is the height from 8 to the curve, which is the radius of each circle, because each cross-section only goes from the line y equals 8, or the radius of each cross-section only goes from the line y equals 8 down to the tip of the curve. So that distance would be 8 minus the equation of the curve. So then the area of each cross-section would be pi times r squared. So it's pi times all of that quantity squared. So then the volume is just the accumulation of all of that area. And also notice that the line y equals 8 intersects the curve x squared plus 4 at -2 and 2. And again, if you needed to find that, you could find those points of intersection. You know, if the graph wasn't given to you, by simply setting them equal to each other. And then you'd get x squared equals 4, and then you'd get x equals plus and minus 2. And then that's how we know to integrate from -2 to 2. So we're going from this point of intersection to that point of intersection, and we're integrating all the areas of all the circles. And then with respect to x. So let me simplify this just a little bit. So pi times, so this would become 8 minus x squared minus 4, so 4 minus x squared, quantity squared, and then dx. So that's the setup of the integral, but fortunately this problem allows us to use a calculator to evaluate, so we'll just plug this into FNINT. Okay, so we will do, let's see, I have to read what it says again. So it's pi parentheses 4 minus x squared quantity squared. So there's that. We're integrating with respect to x from -2 to 2. And so we get approximately 107.233. And that's units cubed, and that was by FNINT. So we always want to state that whenever we are solving an integral with a calculator. I'll put this right here. Okay, so that's pretty much it for the examples for using DISC method. And I hope that you are enjoying your spring break, or if you're watching this at the end, I hope you had a wonderful break. We're going to work with a couple practice problems of these on Monday, and I will see you then. Bye-bye.